Welcome to Module 3 of Middle School Science Praxis Prep. We'll be covering physical science in this module, and this module is a partnership with TLC Tutoring Co. and Arkansas State University. First of all, we want to start with the structure and properties of matter. Now, in the physical sciences, matter is any substance that has mass and takes up space. There are a few things that actually have mass and take up no space, and things that take up space and have no mass. Matter must have both. But all objects around you that you can touch and interact with are composed of atoms, and those are made up of subatomic particles, which are composed of even smaller particles. This basic structure holds true for virtually all matter in the universe. The properties of matter that we're going to be discussing and looking into are any trait that can be measured. And there's some ones here like the object's density, its color, its mass, its volume, its length, its malleability, its melting point, its hardness, odor, temperature, and more. The properties help us define and understand all the types of matter around us. Now, matter exists in three main states in our universe, and each are made of individual particles that behave differently depending on the state of the matter. So, first would just be solids. The matter particles are tightly packed and usually in some sort of a regular pattern. And the particles do move. They vibrate, but only slightly. And they don't move, right? If you have something solid and you set it on a table, it stays there. Now, it is still moving, it's just not moving around. Now, liquids, by comparison, the particles are still pretty close together, but they don't have any regular arrangement. So your coffee in your cup will vibrate and move around and slide past each other and slosh inside the cup. That's how we identify a liquid. Now, gases, again, same particles, but they are well separated and they don't have any regular arrangement. The particles vibrate and move freely at high speeds, and they expand to fill out space that they are placed in. Now, each of these states are affected by their surrounding conditions. So specifically, temperature causes changes in the behavior of these phases. The particles change when you change the temperature. So each state has the particles move faster if the temperature is increased and more heat energy is added. More energy, more movement. The faster it goes, the more energy. And this is the particle theory of matter. And if enough heat energy is added, the phase will change from a solid to a liquid and then to a gas if the particles gain more and more energy. And in the same way, if you remove the energy from refrigeration or cooling, it would move from a gas to a liquid to a solid. Now, as we said, when enough energy has been absorbed by or released from matter, it can change its phase. So if we're talking about gaining heat energy, we would start with melting, that's solid to liquid, then evaporation, liquid to gas, or you can have sublimation, when you go solid straight to a gas. So the big one things is like a regular ice cube is melting, boiling water is evaporation, and sublimation is like dry ice, where it goes frozen carbon dioxide and it becomes a gas immediately with no liquid. Now, for losing heat energy, that the energy is absorbed outside the matter, you have freezing, liquid to solid. So freezing an ice cube in your freezer. Condensation would be, gas to liquid. So that's morning dew on the grass when you walk outside. There was moisture in the air and it condensed onto the grass. And then deposition is a gas to a solid. So this would be like frost crystals for a heavy freeze, where you get those little fuzzy crystals on your car. Often that is the moisture in the air went straight to a solid when it's cold enough. Now, we talked about all these changes happening. This is something called a cooling or heating curve. So this is used to see the temperatures and pressures where phase changes will occur. So consider this water curve. This curve is designed to show you water behaving at different points. So you have water being heated as a solid, and see the temperature is rising. Then the ice begins melting, and you see it stops at 0 Celsius. That is the melting point of water. Notice, heat still being added, but the temperature is not rising. It will stay at 0 until all the ice is melted. Then the water begins to heat as a liquid. If you stick it on your stovetop, It's heating as you add more heat to it, the temperature rises until it starts to boil. Now it's vaporizing. You have to keep adding heat to vaporize it, and eventually all the water has become a gas and you can continue heating it. So you just notice that the temperature rises till a phase change begins, and following a phase change, the temperature begins rising again, and on it goes. So let's take a look at a graph here. So here's the situation. Alex places a small beaker of cold water on a hot plate and he heats it for 10 minutes. He took the temperature of the water several times during those 10 minutes and recorded his data. Alex claims that the graph below shows the relationship between the temperature and the time when the water is heated. Which of these statements best explains why the temperature leveled off in section 2 of the graph? So is it that he turned off the hot plate so it didn't get any warmer? The water reached its boiling point, so the temperature no longer increased. An experimental error is caused by the graph to level off because the water temperature should keep going up. Or cold water heats faster than warm water, so once the cold water was at room temperature, it took more than 10 minutes to make it hot. Now, in this one, we'd say the water has reached its boiling point, even though it's not marked on here, is that the temperature will not go up because we know that Alex is continuing to heat for the 10 minutes and he kept taking samples. So the temperature stopped increasing because it was boiling. Now, we've talked a little bit about the particles that are composing our matter. Now we want to classify those different types of particles. So in broad terms, we have elements and compounds. So elements, and this is the term like elemental. Elements are the simplest complete chemical substances. So think oxygen, nitrogen, lithium. Each element corresponds to a single entry on the periodic table, which we'll get into shortly. An element is a material consists of just a single type of atom, and every atom type has the same number of protons. So every atom of carbon has the same number of protons. That's how you know it's carbon. Now, in comparison, compounds are special groups that chemical bonds will link elements together to form more complex molecules called compounds. A compound could have two or more types of elements held together by covalent or ionic bonds, which we'll get into shortly. Now, compounds can be broken down to the individual elements, and that's general chemical reactions. But the elements themselves, it is very difficult to break them down further without putting in large amounts of energy, or without changing the nature of the element. If you start removing protons, it's not the same element anymore. But we'll get more into some of these differences, but broadly, you have elements and you have compounds. Now, as we said, compounds are formed by chemical bonds, and there's three major types. So first is the ionic bond. So this is a bond resulting from the transfer of electrons between atoms. So you get two charged particles, and just like a magnet, once you have two things that are negatively and positively charged, they're attracted and they stick together. So some examples would be HCl, hydrochloric acid, or NaOH, sodium hydroxide, or NaCl, sodium chloride, which is table salt. Now, covalent, instead of transferring the electrons entirely, they're going to share the electrons. So you get slightly different behavior. So say oxygen gas, O2, water, H2O, carbon dioxide, CO2, and methane, CH4. These all use sharing covalent bonds. And finally, you have metallic bonding. So thinking about just metals you're dealing with. The metallic elements share electrons in a grid structure where they are sharing their electrons over large groups of atoms, and it links them in together and makes them very strong. These strong bonds give metals their flexibility and their strength and their thermal conductivity and their luster, the shininess that they have. All this comes because they use this kind of bonding. Now, beyond the individual elements and the compounds, mixtures of matter can also be made. So a mixture is just a group of elements and or compounds that are physically mixed together. Now, mixtures generally can be separated back into their original elements or compounds. You can separate them. Now, generally there are two types of mixtures. There's the homogeneous mixture, which is a fully mixed mixture. It's very consistent throughout. So ocean water and saline and metal alloys. All of these are consistent, the same all the way through. And then a heterogeneous mixture, or a heterogeneous mixture, is an irregular mixture where the composition is not consistent. So this might be sand. If you've ever looked at sand, they're all different sized pieces and they're not exactly the same. Oil and water, or even chicken noodle soup. Every spoonful you get of chicken noodle soup will be slightly different. So it is not a consistent mixture, therefore it is heterogeneous. Furthermore, there are solutions, which is a special type of homogeneous mixture composed of two or more substances. Now, in a solution, you have a solute. That's a substance that is then dissolved into another substance known as the solvent. My go-to example for this is adding sugar to sweet tea. The tea is the solvent and it absorbs the sugar, the solute. But because it fully suspends and they become just one thing, we call that a solution. Now, there's a few just vocabulary words we want to be clear on. So we have what we call a saturated solution. So think about if I keep adding sugar to that tea, right? This solution it'll keep absorbing sugar to a point that the sugar just sits in the bottom of the tea and it won't absorb anymore. At that point, the tea is a saturated solution. So you can't add any more solute. It's done. It can't absorb anymore. And by contrast, the unsaturated solution would be a solution that has maybe a lot smaller amount of solute. So this would be like unsweet tea, and I add a little bit of sugar. I could add a little bit more. I could add a little bit more. That's unsaturated. In the same way, a dilute solution is one where there's a relatively small amount of solute. So think about if I'm brewing tea, right? I'm creating a solution out from the tea bag. You know, we're seeping the material from the tea leaves into the water and creating a solution. So if it's a very weak tea or a very weak cup of coffee, it's a dilute solution. Or if you're drinking espresso, where there's very strong coffee, right? You have a lot of solute in a small amount of solvent. So that is a concentrated solution. So a relatively high amount of solute dissolved in the solution. So let's try a little practice. Let's use our knowledge of matter classification to answer these questions. Is a blueberry muffin a homogeneous or a heterogeneous mixture? Is milk a homogeneous or heterogeneous mixture? And it is a mixture. Is hot tea, and we'll just say just regular tea, not sweetened tea, just hot tea, is it a mixture or is it a solution? And is a bottle of oil and vinegar, for putting on your salad, is that a solution or a mixture? So the blueberry muffin is a heterogeneous. The blueberries are irregular. Every bite you take of that muffin will taste a little different because you don't know exactly how it's going to be made up. Milk, on the other hand, is a mixture of, fat and enzymes and water and all that stuff, but it is homogeneous. Every sip you take of milk will basically be the same, right? Now, hot tea is a solution because the tea extract that comes out of the tea leaves is in solution with the hot water. So that is a solution. It is dissolved into the water. But a bottle of oil and vinegar, the oil is not dissolved into the vinegar in the same way that vinegar is not dissolved in the oil. They are a mixture. That's why if you let it sit there, it'll separate on its own, and you could actually see the two things in the mixture. Now, in a general sense, acids and bases, or acidity and basicity, are two additional ways to classify matter. Now, both acids and bases are very reactive, and especially with each other. So we just want to run through a few characteristics here. So acids generally are described with a sour taste. When something tastes sour, and apples, and when you have like that sour taste, that's because it has high acidity. Same with coffee, things of that nature. In general, acids donate hydrogen ions. That is their chemical behavior. They react with bases to form salt and water. The pH in the pH scale will be less than 7, and a few examples are hydrochloric acid, hydrobromic acid, and what we call sulfuric acid. See, that one has 2 hydrogens that it can donate. Bases, on the other hand, are almost the exact opposite. Now, they have a characteristic bitter taste, so like you're eating bitter herbs or things like that. Those have a strong base level. They donate OH, or what we call hydroxy ions. And they also react with acids to form salt and water, but their pH is going to be greater than 7. So some examples would be sodium hydroxide, NaOH, or lithium hydroxide, or calcium hydroxide. These are three very common bases, and these all work together in different solutions. So let's talk about atomic structure. So we said that all matter is composed of atoms, which are then composed of subatomic particles, smaller than atoms. So you can see in this diagram, this is a helium atom. You can see the three major particles. So the positively charged particles are the protons, and they're red. And then you have the blue ones, which are called neutrons, and they have no charge, but they are both located in the nucleus, in the center of the atom, as well as the negatively charged electrons, which surround the nucleus in an area called the electron cloud. They surround the nucleus with all the electrons of a specific atom. Now, once we've talked about atoms, we start talking about how they can differ. So, first of all, is an isotope. So these are atoms of the same element, which means they have the same number of protons, but different numbers of neutrons. And this changes the weight of the atom, because there's just more mass there. So, for example, if you've ever heard of carbon-14 dating or carbon dating, that tracks carbon-14, which is an unstable variation on carbon. It's an unstable isotope. So carbon-12 is what you think of as just like coal carbon. But both of these carbons have 6 protons, but different numbers of neutron. And again, this is used in carbon dating. So you can see in this picture, carbon-14 has 8 neutrons versus carbon-12, which only has 6. Now that we talked about isotopes, we can talk about ions. So ions are atoms of the same elements, same number of protons, but they have a different number of electrons. Therefore, they have a positive or a negative charge. So an ion that has given up electrons and is now positively charged is called a cation. And an ion that has gained electrons and is now negatively charged is called an anion. So these ions can then be utilized in ionic bonding, because now that they have a charge, like two ends of a magnet, they want to come together. So think about sodium chloride, that's table salt. The sodium is the cation. You can see in this diagram it is giving up one of its electrons to chlorine, because chlorine wants to have a full valence set, 8 electrons. The chlorine accepts that electron and it becomes the anion. So now you can see the chlorine has a negative charge and sodium has a positive charge, and they stick together, just as magnets are wont to do. Now, as we talked about some of these different elements and compounds, we want to talk about the periodic table. So the periodic table, specific information about an element can be directly read from the entries, so they're very useful. They also have specific things that they have in common in each of the rows. So looking at, this is a typical periodic table entry for oxygen. So the first number is the atomic number. That's the number of protons, and that defines the element. Every atom of every oxygen that's ever existed had 8 protons, so we say that defines this. Then in the middle, you usually have the element symbol, which is sometimes comes from Latin, sometimes it comes from the English word. In this case, oxygen is O, because that's a very common one. It was one of the first ones we classified. Now, the atomic weight is the mass of a typical atom. So this is the mass of the protons and the neutrons added together. Now, you'll notice that this is not a round number. That's because this is an average of all the isotopes for this element. So, like we said, isotopes have different numbers of neutrons. So this normally is not an even number. It's a weighted average of all the atoms of oxygen that we've ever studied. Now, here is a typical periodic table. So I want to spend a few minutes talking about this. Now you can see oxygen in the upper right-hand corner, but we're going to hit just a few of these things. So the far left, in rows 1 and 2, you have what we call the alkali and the alkaline earth metals. These are metals, and they want to contribute electrons. So they are very reactive. You know, your sodium, potassium, calcium, strontium, rubidium. These are all very reactive metals that want to react with the nonmetals. In the middle of the chart, you have this transition area, which is sort of pink here, as well as this bottom part, called the lanthanides and the actinide series. These are all various metals that we call the transition metals, where you're transitioning from one side of the chart to the other. These all have very flexible in how many electrons they may want to give up or how they want to behave. Next, you pick up what we call the post-transition metals, and you see they are that kind of gray-green color. So that's aluminum, gallium, indium, and they are just past the transition metals before you get to our next group called the metalloids. That's that medium green color. So that's your boron, your silicon. These are interesting because they have some metal properties, and they have some non-metal properties. We use them a lot in semiconductors because they're not as conductive as metal, but they still conduct, they can still conduct signals. So they're very useful in that way. Then you have the non-metals, which are the kind of bright greens, your carbons, your nitrogen, your phosphorus. These are very reactive with the metals to make different kinds of compounds. Now, row 7 is a special group of non-metals called the halogens. Halogens are very reactive. Fluorine, chlorine, bromine, you've probably heard of many of these. They readily bond with metals, and they are very quick. They aggressively grab electrons because they want to get stable. So they're always grabbing electrons from things around them, and they're very reactive. And on the far right is maybe the best name on the entire table, is the noble gases. And we mean noble not that they're better, but that they don't like to mess around with all the other things on the chart. So your helium, your neon, your argon, krypton, xenon, radon, all of these are very not reactive. They do not like to react. They like to be on their own and they float around. This is why a balloon full of helium won't burn. If you if you stuck a hot poker in it, it won't do anything. It'll just pop the balloon. But a balloon of hydrogen will burst into flame because hydrogen is very reactive. So the table can give us basic information about all the different types of elements and how we might expect them to behave. So let's do a little practice now that we've gotten more familiar with the periodic table. So I have here the summary for cadmium, which you can see is a very lustrous metal. So how many protons does an atom of cadmium contain? How many neutrons does an atom of cadmium-114 contain? And if an atom of cadmium had 46 electrons, what would be the ionic charge of that cadmium atom? Now, how many protons? You can see in our listing over here that it says the upper left is the atomic number, 48 protons. Every single atom of cadmium has to have 48 protons or it's not cadmium. Now, the neutrons, cadmium-114, recall that this is an isotope, right? This tells us the overall atomic weight. You can see the average weight in the listing is 112.4. This is cadmium-114. So 114 is the overall weight. So that is the overall weight minus 48. That's the number of protons, which says that there must be 66 neutrons. And then we said if I had an atom of cadmium that had 46 electrons, if there are 46 electrons and each of them has a negative charge, and 48 protons, each with a positive charge, we would end up with a +2 charge on this atom of cadmium. And that completes physical science review for Module 3. Congratulations! So Module 4 will go deeper to cover chemical reactions. Thank you so much.